Adding and subtracting radicals is very similar to adding like terms. If you recall, if we have two terms that are being added together, they're considered like terms if not only do they have the same letter, but the same letter or variable with the same exponent on that variable. So these are considered like terms. Therefore, we're allowed to add the coefficients, but we don't change the exponent on the variable. In other words, you have 2 of these and 3 of these, and now you have 5 of these. So when you get into radical expressions, it's the same situation and same rules apply. So if you have 2 of these plus 3 of these, you now have 5 of these. You would not be able to add these unless both the index was the same and what's under the radical is the same. If so, then you consider this, you have 2 of these plus 3 of these, so now you have 5 of these. That's one way of thinking of it. Now if you look at these radicals, it looks like they're not like radicals, and therefore you might think that you just have to leave them and not simplify them any further. But if each radical could be simplified, in other words, you could take a perfect square or some numbers out of the radical and leave some inside, you may find that they end up being like radicals that could be added or subtracted. So let's see. I wrote all the prime factorizations off to the side because that's the way I like to do the breaking apart of the radical. So 12 is 2 times 2 times 3. 75 broke down to 3 times 5 times 5. And square root of 3 is just 3 times 1, so it's prime, and we leave him alone. Now, again, if you need review on how to break apart a radical, you can go to my video on simplifying radicals. So what we have here is we have 2 2's and 2 5's, and anytime you have a pair on a square root, you can pull that number out. One of them disappears on the way out and one stays inside. Second one, we have a pair of 5's, so a 5 can come out, and when it gets square rooted, you lose one on the way out, and you end up with the 3 staying inside. And we'll just leave that last one the same. So now you can see that these all have the square root of 3 in them. So they are like terms now, or like radicals. And so we can think of this as we have 2 of these, we have 5 of these, and we have 1 more of these. And so 2 plus 5 minus 1 is 6 square root of 3. So if you take 2 of these and you add 5 of these, you get 7 of those, minus 1 of those, you get 6 of those. So let's try the same thing on some cube roots. Cube roots just mean you have to have 3 of something before it can come outside the radical. So let's see what we have here. I'm just going to save space and mark them off over to the side. So we have a 5, and a 5, and as long as we have 3 of those, that means we can pull it outside the cube root. But you only write it once outside the square root. Then the remaining guy has to stay inside the cube root. On 54, we end up with 3 3's, and when we have 3 of them, we can pull that number out, and the other 2 has to stay inside. And then finally on 16, we have a set of 3 2's, means we can pull a 2 out, but we also have a leftover 2 that has to stay inside. Now you have the cube root of 2 on all of them, so I have 5 of these, I have 3 of these, minus 2 of these, that's 8 of those, minus 2 of those makes 6 of those. So you don't ever change the actual radical when you're adding and subtracting. It'll stay cube root of 2 Just like when we had 5x plus 3x minus 2x, we would call that 6x. It's the same idea. You can't add them unless they're like radicals, and once you add them, you don't change the radical.